This chapter explores the question of why supercharging is used in internal combustion engines. It starts by taking a quick look into the past to show how supercharged petrol engines have evolved at Mercedes-Benz from their first beginnings right up to the present day. The next section gives an overview of the study content of this two-part series of CBT programs. The chapter concludes by discussing the advantages of supercharging petrol engines when compared to conventional naturally aspirated engines. The first ever models from Mercedes to be fitted with compressor-type supercharged petrol engines were developed shortly after the First World War by Paul Daimler, the son of Gottlieb Daimler, who was the technical director at Daimler Motorengesellschaft at that time. The first series-produced passenger cars with compressor-type supercharged engines hit the showrooms just a few years later. The compressor fitted in the engines was the Roots blower, which was first patented by the Roots brothers in the US in 1860 and had already been used to improve supercharging in aircraft engines. The compressor blower, which was a highly elaborate piece of engineering for standards at that time, featured predominantly in high-performance and luxury cars, such as the 630K built from 1926. Just 1 year later, a second compressor-powered model series from Mercedes caused a sensation in the motoring world. The sports cars bearing the model designations Sport, Supersport, Supersport Short, and Supersport Short Light, which would go on to dominate the world of motorsport until well into the 1930s. The 8-cylinder 500K and 540K compressor-powered models that went into series production in 1934 raised the bar again. They succeeded in harmonizing high performance on the one hand with unprecedented standards of smoothness on the other, even outclassing the Mercedes-Benz 770 Grand Mercedes models built between 1930 and 1943. After the Second World War, supercharged petrol engines became the preserve of the motor racing elite. It wasn't until the 1990s that compressor-charged and turbocharged engines made a comeback in series-produced models from the Mercedes car group. Now, let's take a look at what you are going to learn in this two-part series of programs. This program, Part 1, starts by explaining the supercharging effect of a variable intake manifold, taking the example of the 272 V6 engine. It also concentrates on exhaust gas turbocharging, which is illustrated using the example of the 160 three-cylinder engine, as well as the bi-turbocharged 275 and 285 12-cylinder engines. In the second part of this CBT series, you will learn about compressor-type supercharging, using the example of the 271 four-cylinder engine. Part 2 also examines the technical differences in the method of compressor-type supercharging featured in the 112 and 113 engines from AMG. Why is supercharging actually used in petrol-powered engines? Let's take a closer look at the reasons for supercharging. In principle, the power output and torque of an internal combustion engine are determined by the quantity of fuel and air in the cylinders at the end of the compression stroke. Maximum use is made of the fuel's potential energy if there is sufficient oxygen to burn each molecule of fuel. As air only contains around 20% oxygen, however, a relatively high proportion of air must be added to the fuel. The rate of airflow required for this depends on a number of factors. The rate of airflow basically depends on the engine speed, the displacement, and the density of the air being fed into the engine. Power can be boosted both by increasing the overall displacement or by raising the maximum engine speed. If neither piston displacement nor engine speed can be altered due to design reasons, however, the only other way of boosting power is to increase the air density. This can be achieved with the assistance of supercharging systems, such as a compressor or exhaust gas turbocharger, for example. Another reason for supercharging engines is that small supercharged engines, as well as achieving an identical power output to naturally aspirated engines with a larger piston displacement, are also more fuel efficient, meaning that they emit fewer pollutants into the atmosphere. This stems from the fact that smaller engines are lighter, with lower accelerated masses and less friction. This is neatly illustrated by comparing the compressor-charged C200 model with the naturally aspirated C240. This comparison demonstrates that although the output and torque figures are virtually identical, the supercharged engine, with a lower displacement, displays lower fuel consumption figures. Manufacturers' efforts to reduce the fuel consumption of motor vehicles by using smaller engines without compromising on power output in any way are referred to as downsizing. A further factor in favor of downsizing is the tax breaks that exist in some markets for vehicles with engines having smaller displacements. Let's summarize what we have learned in this chapter. A brief look at the history of supercharged petrol engines at Mercedes-Benz showed you how they have evolved from their first beginnings right up to the present day. You also discovered the primary reasons for supercharging internal combustion engines: boosting power output and downsizing. This chapter examines the underlying principles of supercharging in petrol engines. It starts by explaining the meaning of the term cylinder charge. The next section demonstrates why supercharged engines achieve a superior cylinder charge compared to naturally aspirated engines. You will also be introduced to the design measures which are implemented to optimize cylinder charging. The chapter concludes with a look at why supercharged engines are fitted with intercoolers. The term cylinder charge refers to the mass of gases present in the cylinder after the intake stroke has been completed and the inlet valves have closed. This mass consists of both the fuel-air mixture which has been drawn into the cylinder as well as the residual gas, i.e. the exhaust gas which remains in the cylinder after the combustion gases have been expelled. The theoretical maximum charge of a cylinder is dictated by the size of its combustion chamber. This is the space enclosed by the cylinder wall, cylinder head, and the piston crown, and its size changes constantly during each stroke. The combustion chamber is at its largest when the piston is at bottom dead center, BDC. Conversely, the volume is smallest when the piston reaches top dead center, TDC. The maximum size of the combustion chamber is the swept volume plus the clearance volume. The cylinder charge is impaired by flow resistance in the intake system and shorter valve opening times at higher engine speeds. Consequently, the maximum cylinder charge is not attained as the mass of gases that is drawn into the cylinder is less than the theoretical maximum mass. This mass spreads evenly throughout the combustion chamber. The ratio of gas mass actually drawn into the cylinder to the theoretical maximum cylinder charge is called the delivery ratio. For naturally aspirated engines, the delivery ratio is between 60 and 90%, depending on the engine speed. Supercharged engines, on the other hand, are capable of achieving a charge efficiency of over 200%, as the gas is delivered into the combustion chamber under pressure. A variety of measures can be used to improve the cylinder charge. These include designing the intake system to be as efficient as possible, fitting multiple inlet valves for each cylinder with intake ports of large area, adapting the valve timing to the engine speed, and designing the shape of the combustion chamber for optimum combustion. Once these possibilities for optimization through design measures of the actual engine components have been fully exploited, it is still possible to increase efficiency by boosting the pressure by means of a turbocharger or a compressor. When gases are compressed by a turbocharger or a compressor, not only the pressure increases, but the temperature too. This physical effect will be familiar to anyone who has pumped up a bicycle tire with an air pump, for example. Because the air molecules are pushed together, the same thermal energy is distributed over a smaller space. This results in a rise in temperature. As you have seen, when air is compressed, there is a link between the change in pressure and the change in temperature. The same effect is produced when air pressure is increased using a compressor or turbocharger. However, an increase in the temperature of the charge air would reduce the cylinder charge. This is because the charge air expands as its temperature increases, meaning that it occupies a greater volume than at its initial temperature. This problem can be solved by cooling the pre-compressed air before it enters the cylinder. Let's review the key points of this chapter. You now know that the cylinder charge is the mass of gases present in the cylinder after the inlet valves have closed, and that the term delivery ratio refers to the ratio between the mass of the gas that is actually drawn into the cylinders and the theoretical maximum mass of gas. You are also now familiar with the measures which can be implemented to optimize the charge efficiency of cylinders, such as designing the intake system to be as efficient as possible, fitting multiple inlet valves for each cylinder with intake ports of large area, adapting the valve timing to the engine speed, and a combustion chamber of optimum shape. The cylinder charge can also be increased by using a turbocharger or compressor to boost pressure. In this case, an intercooler provides an additional means of improving the cylinder charge. This chapter deals with the main aspects of variable intake manifolds. This includes a look at the fundamental design of the intake system fitted in naturally aspirated engines, and the resonating pipe effect, which helps to improve cylinder charging. You will learn about the relationship between intake manifold length and engine speed, and will find out more about the structure and operation of the variable intake manifold fitted in the 272 engine. In a naturally aspirated engine, the air is transported with the help of the intake system. This system comprises the following components: an intake hose, by means of which air is drawn in from the vicinity of the radiator opening, thus limiting entry of water and dust particles; an air cleaner, which protects the engine from dirt and dust, as well as various silencers. Some engine series also feature a hot film air mass sensor, which registers the mass of air drawn in. This is followed by the throttle valve actuator, which can restrict the flow of intake air by moving the throttle valve into an oblique position. The air then flows to the intake manifold and the individual intake pipes before finally reaching the inlet ports and inlet valves in the cylinder head. When the engine draws air in, vibration occurs in the intake system. These oscillations can be made use of to improve the charge efficiency of the cylinders. The 272 engine, for example, harnesses the resonating pipe effect which occurs during the intake stroke. Let's take a closer look at what happens during this process by looking at an individual cylinder. The downwards motion of the piston produces a negative pressure wave. This wave travels away from the combustion chamber along the intake pipe, being reflected back by the air in the intake manifold. This produces a positive pressure wave, which travels back towards the combustion chamber, filling the cylinder during the intake cycle thanks to the increased pressure. The time the pressure wave takes to travel through the intake pipe depends on the pipe's length. The longer the pipe, the longer the pressure wave will need to travel from the cylinder to the intake manifold and back to the cylinder again. In order to achieve a supercharging effect, the pressure wave must reach the cylinder before the inlet valve closes. As engine speed increases, however, the valve opening times shorten. Decide for yourself which of the curves shown here correctly depicts the relationship between engine speed and intake pipe length. Accordingly, there is a relationship between intake pipe length and the engine speed. The higher the engine speed is, the shorter the intake pipe should be to ensure that the pressure wave arrives before the inlet valves close. At lower engine speeds, on the other hand, long intake pipes are preferable, as the pressure wave has sufficient time to reach the cylinder before the inlet valves close. In order for cylinder charge efficiency to be optimized over a wide range of engine speeds, a variable intake manifold system is used. Have a look at the structure of a variable intake manifold system, taking the 272 engine model as an example. This is a two-stage variable length intake manifold, which is designed in the form of a spiral and whose effective length can be shortened by means of a flap. On the 272 engine, the position of the flap in the variable intake manifold changes depending on the engine load and speed. At idling speeds under low engine load, the flap stays open over the entire engine speed range. In this situation, the air flows through the short intake manifold pipe. The flap position only changes at higher engine speeds in a certain range of engine loads, as it is only then that varying the intake manifold length has a beneficial effect on the power output being required from the engine. Here you can take a closer look at the working of the variable intake manifold at high engine loads. At high rev speeds, the adjustable flap opens to shorten the distance travelled by the air. The long intake tract is used at medium engine speeds. The adjustable flap is closed in this case. At low engine speed, the flap is also open, as design limitations preclude the extremely long intake manifold tract that would otherwise be required. In doing this, the only benefit gained is that of the low flow resistance resulting from the open flap. You may already have heard that the 272 engine is fitted with an additional flap. This flap is a tumble flap, located in the intake ducts, which is also referred to as a swirl flap. Tumble flaps are fully retractable flaps located in the intake ducts. At part load operation, the flaps pivot open to change the flow characteristics of the intake air. This has the effect of producing swirls in the cylinder's combustion chamber, which help to mix the fuel and air together more thoroughly. This optimizes combustion, which in turn lowers fuel consumption. This chapter concludes with a look back over the key points. You are now familiar with the basic structure of the intake system used in a naturally aspirated engine, including the individual components, from the intake hose right through to the inlet valves. The resonating pipe effect can be used to improve cylinder charge efficiency. Long intake manifold pipes are used at low engine speeds and short pipes at high engine speeds. You also became acquainted with the spiral-shaped configuration of the intake pipes fitted in the two-stage variable intake manifold system featured on the 272 engine. This chapter studies the exhaust gas turbocharger. It starts by examining the structure of the intake system on turbocharged engines. You will be introduced to the intercooling system featured on the 160 and 275 engines, and will find out how a turbocharger is structured, taking the example of the 275 engine. A further section deals with the cooling and lubrication of the turbocharger. The chapter concludes with a look at the workings and method of operation of the turbocharger fitted on the 275 engine. Within the Mercedes car group, engines featuring an intake system with turbocharger include the 160, 275 and 285 engines, for example. Here you can see the design of the intake system, taking the 275 engine as an example. After passing through the intake air hose, the air enters the air cleaner, which purifies it by removing water, airborne dirt and dust particles. The now purified air is drawn in by the turbocharger's compressor turbine wheel. As the air heats up when it is compressed by the turbocharger, it has to be directed through the intercooler afterwards to cool it down again. On this V-type engine, the air ducting has a twin-tracked design. This overhead view of the intake system shows the twin intercoolers. Click on one of the intercoolers to track the subsequent path of the intake air. As you can see, each bank of cylinders has a separate air cleaner, turbocharger and intercooler. The Y connection directs the cooled air emitted from the intercoolers to the throttle valve actuator. From there, the pre-compressed charge air is fed through the intake manifold into the individual intake pipes, where it finally reaches the inlet valves. The intercooler featured on the 160 engine used by the Smart uses air-to-air cooling with engageable forced air circulation. The intake air that is compressed by the turbocharger is cooled inside the intercooler. The intercooler is located above the transmission and is cooled directly by the airstream. When the intake air reaches a certain temperature, the electrically powered fan cuts in. This fan helps to cool down the intake air. Now take a look at the intercooling system fitted in the 275 engine. The charge air's heat is transferred to the coolant that flows through the intercooler. The heated coolant flows to the low-temperature radiator. This is therefore an indirect form of intercooling with a separate low-temperature cooling circuit. Water cooling achieves higher efficiency than air-cooled intercoolers. The heat absorbed by the coolant is in turn dissipated into the atmosphere inside the low-temperature radiator. The recirculation pump is used to recirculate the coolant. It is engaged and disengaged by the engine management unit as required. When carrying out maintenance work on the low-temperature cooling circuit, it is important to follow the special maintenance and repair guidelines contained in WIS. Take a closer look at the basic structure of a wastegate turbocharger together with its principal components as fitted in the 275 engine by studying this schematic diagram of a cylinder. The compressor wheel and turbine wheel are connected to one another by means of a common shaft. A further key component is the boost pressure regulating valve or wastegate valve, which the vacuum cell acts upon via a control rod to open a bypass duct that leads around the turbine wheel. A number of engines, including the 275 model, are equipped with an additional blow-off valve, which enables the air to bypass the compressor wheel. This serves to minimize turbocharger noise and optimizes turbocharger response when the driver suddenly comes off the throttle. Quite apart from this, All turbocharged engine models are fitted with an intercooler. The throttle valve actuator is only used to throttle the air supply when the air is at boosted pressure. The shaft casing of both turbochargers on the 275 engine is connected to the engine's coolant system. Two connections in the crankcase direct the coolant to the turbochargers, where it flows into the shaft casing's cooling jacket at the bottom and out again at the top. While the engine is running and after it has been switched off, the flow of coolant through the turbochargers is aided by the thermosiphoning principle. This makes use of the difference in density between hot and cold water. Hot water has a lower density, causing it to flow upwards. To ensure that the rotating parts are properly lubricated, the turbochargers are connected to the engine's lubricating oil circuit. The lubricating oil flows in the opposite direction to the coolant. The lubricating oil is taken from the crankcase's main oil duct, flows through the shaft casing, feeds the special friction bearings, and then returns to the bottom section of the crankcase. Watch now how the turbocharger works, using the 275 engine as an example. During the exhaust stroke, the exhaust gases from each bank of cylinders are directed through the exhaust manifold to the turbine wheel. The exhaust gas's flow energy makes the turbine wheel turn. The turbine wheel drives the compressor wheel it is attached to by a shaft at the same rotational speed. The compressor wheel compresses the fresh air that is drawn in before feeding it through the intercooler and into the intake duct. The charge pressure regulation valve is used to direct a lesser or greater proportion of the exhaust flow around the turbine wheel, enabling boost pressure to be adjusted and restricted as required. Boost pressure is available from an engine speed of around 1,500 revolutions per minute. Below this speed, the turbocharged engine has the same operating characteristics as a naturally aspirated engine. Maximum boost pressure, the pressure above standard atmospheric pressure, is around 0.9 bar in the 275 engine, for example. The turbocharger converts the energy derived from the engine's exhaust gases into mechanical energy for driving the compressor. The exhaust gases are directed through the cross-section of the turbine inlet and onto the turbine wheel's blades at a tangent, producing both a pressure and a temperature gradient between the inlet and outlet points. The turbine's power increases with increasing pressure gradient. That is when higher engine speeds cause more and more exhaust gas to build up ahead of the turbine. Likewise, the inlet cross-section influences the flow speed at the turbine wheel, although any increase also has the effect of raising the exhaust gas back pressure in the exhaust manifold. Driving the turbine wheel causes a loss of energy of the exhaust gas, causing its speed to drop. It is forced deeper into the turbine blades by the exhaust gas further upstream before it eventually exits the turbine in an axial direction. Let's summarize the main points of this chapter. Taking the example of the 275 engine, you were introduced to the structure of the air intake system fitted in engines with exhaust gas turbochargers. The charge air is either cooled by means of an air-to-air intercooler or by an indirect form of cooling featuring a separate low-temperature cooling circuit. You then learned about the basic structure of a turbocharger, again taking the 275 engine as an example. Cooling is carried out by connecting the shaft casing to the coolant system. Similarly, lubrication is taken care of by means of a connection to the engine's lubricating oil circuit. You then saw how a turbocharger operates. This chapter deals with the matter of turbocharger regulation. It starts with a look at the system of pneumatic charge pressure regulation used in the less powerful variants of the 160 engine model. This serves as the basis for the electronic charge pressure regulation system featured in the more powerful engine models in the 160 series, as well as in the 275 and 285 bi-turbo engines. A further section deals with how the turbocharger is protected from over-revving. Finally, you will find out more about how the blow-off valve works in the bi-turbo engines and about the advantages it has for various vehicle operating states. The charge pressure produced by a turbocharger can be regulated in a number of different ways. Charge pressure regulation in the 160 series petrol engines fitted in smart models up to 37 kilowatts, for example, is carried out pneumatically. The higher powered variants of the 160 series engines, as well as the 275 and 285 bi-turbo engines, on the other hand, are fitted with an electronic charge pressure regulation system that is based on the pneumatic regulation. First, let's take a look at pneumatic regulation. This regulation is carried out by means of a bypass duct around the turbine wheel, which is opened and closed by the action of the charge pressure regulation valve. This valve is actuated by the vacuum cell acting via a control rod. Watch what happens when the driver demands more power from the engine. You should have been able to make the following observations regarding pneumatic charge pressure regulation. When the driver demands more power from the engine by depressing the accelerator pedal, the throttle valve opens further. As the engine speed increases, the engine draws in the charge air, causing the pressure to drop in the intake duct. This pressure drop acts on the vacuum cell's diaphragm via the connecting line. If the pressure drops below a certain threshold, the spring closes the charge pressure regulation valve. If this valve is closed, the turbine wheel is driven by the full exhaust gas flow, accelerating the turbocharger to its maximum speed. The charge pressure and, as a result, the engine's power output rise accordingly. Once the required load state has been reached, the driver eases off the accelerator pedal and the engine load drops again. As a result, the throttle valve closes and the charge pressure builds up behind it. This charge pressure acts on the diaphragm via the connecting line to the vacuum cell. In turn, the diaphragm counters the force of the spring to open the charge pressure regulation valve. This allows a portion of the exhaust gases to bypass the turbine wheel, which has the effect of decelerating the turbocharger. Now take a look at the electronic method of charge pressure regulation used in the more powerful variants of the 160 engine, as well as in the 275 and 285 bi-turbo engines. First, see how the electronics cut in to regulate the charge pressure. This is the task of the pressure transducer for charge pressure regulation, which is triggered by a PWM signal emitted by the engine control unit. Based on the signal received from the control unit, the pressure transducer relays a variable pressure to the vacuum cell. This pressure can be any value between the full charge pressure and the surrounding atmospheric pressure. First, take a look at what happens when the full charge pressure acts on the vacuum cell. The pressure transducer opens fully the connecting line between the compressor side of the compressor wheel and the vacuum cell's diaphragm chamber. This allows the full charge pressure to act on the vacuum cell's diaphragm, enabling the charge pressure regulation valve to open even at low charge pressures. Now watch what happens when the situation is reversed. The pressure transducer vents the vacuum cell to the atmosphere. As the charge air cannot act on the cell in this state, the spring closes the charge pressure regulation valve again. The turbine wheel will now be driven by the full exhaust gas flow, increasing charge pressure to its maximum value. As you can see, the pressure transducer used for electronic charge pressure regulation enables the pressure in the vacuum cell to be optimized for any engine load state. In this way, the target charge pressure requested by the driver can be quickly attained. This charge pressure varies depending on the engine load and a number of other influencing factors. In the case of electronic charge pressure regulation, the pressure transducer for charge pressure regulation is triggered by a pulse width modulated signal sent from the control unit. PWM signals have a variable pulse duration and a fixed cycle duration. The ratio between the duration of a pulse and the cycle duration is known as the duty ratio. This ratio is stated as a percentage. For example, on engines fitted with electronic charge pressure regulation, the full charge pressure will act in the vacuum cell if the duty ratio is lower than 5%. Conversely, the vacuum cell is vented to the atmosphere if the duty ratio exceeds 95%. The engine control unit can relay any duty ratio between these two values to the pressure transducer, allowing for optimum regulation of the charge pressure. Electronic charge pressure regulation in the bi-turbo engines draws on numerous input variables. One of the key variables is the engine load. This is calculated using the signal from the pressure sensor downstream from the throttle valve. The actual value for the charge pressure is registered by the pressure sensor upstream from the throttle valve. Based on the ratio between the charge pressures upstream and downstream from the throttle valve, the control unit is able to compute the target charge pressure. The other input variables are only used by the engine control unit to correct charge pressure regulation in specific operational states. These additional variables include, for example, the intake manifold pressure upstream from the compressor. This pressure is registered by the pressure sensor downstream from the air cleaner, allowing for a direct comparison with the current charge pressure. There is a further pressure sensor incorporated into the engine control unit, which records the current ambient pressure. The charge air temperature pickup senses the current temperature of the charge air at the throttle valve actuator. Combining this signal with the signal from the pressure sensor downstream from the throttle valve allows the air mass to be calculated. The temperature pickup also monitors the operation of the intercooling system. The 275 includes a number of additional special features. In order to prevent the turbocharger from over-revving when driving at altitude or when the air cleaner is clogged with dirt, the maximum charge pressure is calculated based on the ratio between the pressure upstream and downstream from the compressor, and then applied by the electronic charge pressure regulation system in accordance with the engine performance map. This calculation is performed with the aid of the pressure sensor downstream from the air cleaner and the pressure sensor upstream from the throttle valve actuator. Whenever the engine is overrunning or the driver comes off the throttle suddenly, the throttle valve is closed. Due to the inertia of the shaft, compressor wheel and turbine wheel, the turbocharger continues to rotate for a short time, producing a certain boost pressure that builds up at the compressor wheel. What consequences do you think this has for the operation of the turbocharger? The back pressure which forms at the compressor wheel slows the wheel down. This can give rise to an undesirable pumping noise known as blow-off whistle. The next screen illustrates the design measures which can be implemented to eliminate this effect. In order to prevent the closed throttle valve having a detrimental effect on operation, and to allow the compressor wheel to continue to rotate unhindered when the engine is overrunning, The turbocharger units fitted in the 275 series engines are each fitted with a blow-off valve. This is connected to the intake manifold via the blow-off valve boost control. During normal turbocharger operation, the charge pressure acts on the blow-off valve diaphragm chamber, keeping the valve closed. Now watch how the valve works when the engine is overrunning. In this case, the blow-off valve boost control is actuated by the engine control unit. When actuated, the boost control valve opens a connection to the vacuum reservoir, while the connection to the intake manifold shuts. This creates a vacuum in the blow-off valve diaphragm chamber, causing the valve to open. The pre-compressed air can now be pumped from the compressor side of the compressor wheel to the intake side. The bypass that this creates allows the back pressure at the compressor wheel to be dissipated instantly, thereby preventing any undesirable blow-off whistle. Quite apart from eliminating undesirable pumping noise at the compressor wheel, the blow-off valve holds a further benefit. When the driver demands power from the engine again, the throttle valve is reopened. The blow-off valve boost control restores the connection to the intake manifold, causing the charge pressure to act on the blow-off valve diaphragm chamber and closing the valve in the process. As the turbocharger was running at zero load when the blow-off valve was open, its rotational speed has barely dropped. This improves turbocharger response, allowing charge pressure to be built up more rapidly. In conjunction with turbochargers, reference is often made to the turbo lag, which occurs when the throttle is opened again after the engine has been overrunning. Turbo lag refers to the time needed by the turbocharger to build up a noticeable charge pressure. In the case of the 275 engine, however, the presence of the blow-off valve and the adequate exhaust flow in all operating states means that there is no notable loss in power. Let's summarize the key aspects of turbocharger regulation. The 160 series engines from Smart with a power output of up to 37 kilowatts feature a purely pneumatic system of charge pressure regulation. The more powerful versions of the 160 engine, as well as the bi-turbocharged 275 and 285 engines on the other hand, feature an electronic system of charge pressure regulation which is based on the pneumatic method. To enable it to regulate the charge pressure, the engine control unit makes use of numerous input variables which are recorded by means of various sensors. In order to prevent over-revving, the maximum speed of the turbocharger fitted in the 275 and 285 engines is limited when driving at altitude or when the air cleaners are clogged with dirt. The blow-off valve opens a bypass around the compressor wheel to prevent the undesirable pumping noise which can otherwise occur when the engine starts to overrun or the driver comes off the throttle suddenly. The inclusion of the blow-off valve also improves turbocharger response when the throttle is opened again.